Hello everyone, welcome to the troubleshooting lecture on how to troubleshoot deep learning models. By the end of today's lecture, I would hope that you will understand better what to look for when developing deep learning models, the iterative process of developing the models and increasing their complexity. So how do you start from a very small model that is easy to understand to something that is more complex with the capabilities that you might want to achieve? And how do you read performance curves and what to expect between train, test, and validation curves? So just as a disclosure, this lecture is highly inspired by Josh Torbin's Troubleshooting Deep Neural Networks talk, which is a really fantastic talk. But this is actually a subject that has been going on for a while based on subjects of the Andrew Ng's book, Machine Learning Yearning, which is a very practical book on tricks of the trade of how to use and optimize for machine learning models, but also this incredible thread that Andrej Karpathy has published on Twitter, which has resulted in literally hundreds and thousands of researchers providing tricks of small little things that they do and that they've observed that have resulted in a compendium of multiple different things that you can improve and how to better develop deep learning models. So all of these researchers that I've been talking about, Josh, Andrew, and even people like Andrej, they're really incredible researchers. And today's lecture is really a form of flattery by trying to imitate some of the things that they themselves have brought together into a single lecture. So why do we need to troubleshoot deep learning models? Deep learning models have this premise that they somehow are this black box that you just give data to the black box and the black box works out of the box, which is a really interesting thing to say because clearly the black box, there's nothing special or black about it. It's just, yes, it is a very complex software stack. And because it is a software stack, it does have issues and we need to be aware of those issues. So what we need to figure out is how do we create a black box or a model that is actually able to just take data and learn from that data in the best way possible. And how do we make sure that that model has the capabilities that we want, given that there is a large software stack behind the scenes that we need to manage? There was this post again by Andrej Karpathy, where he was talking about debugging as a process where you first start with something that doesn't even compile, that doesn't link, the code then segfaults, then it gives you all zeros, then it gives you the wrong answer, and then maybe it works. And what's interesting here is that it shows that debugging is a process. It's a process where nothing is working at the beginning, and then things start working one by one, but until the very end, only then it works. So until the last step, until you build the full puzzle, until all of the issues are solved, things do not work at all. It still gives you the wrong answer until the very last step, except when you fix the last bug and then everything works out. And the premise here is even worse in a deep learning setting. So again, as I was saying, deep learning has a large software stack with many moving parts, and many times is enough for one of those many moving parts to be wrong for the models to not perform as you would expect. So this is something that you always have to take into account when training your models, is that all of the pieces of the puzzle need to work well for the model to do what it's supposed to do. And the reason that we need to talk about deep learning and troubleshooting is that something that is quite common sentiment across practitioners is the fact that you spend 10 to 20% of your time deriving the mathematics and maybe implementing the method you want to implement. But most of the time is going to happen with debugging the code and making sure that things are tuned properly, that you understand the behavior, that you can do hyperparameter tuning, a series of experiments. And this is without even taking into account all of the data issues that you might face. So deriving the mathematics and implementing a model is actually a minuscule part of the work you need to do. And the biggest part is actually going to be the debugging part, because that's the part where you truly understand the models. So the first thing that we need to think about is your plan, let's say, is to develop a method and you want to reproduce the result that someone has presented in a paper somewhere. And you see this plot here on the left, which is the performance of the method that was proposed in this paper. And the training curves look really beautiful. They have these kind of staircasing effects, probably due to changes in the learning rate scheduling. And they see this beautiful performance between the 18 and the 34 layer model. They claim that the 34-layer model is the best, and they end up with a performance just below 30% of error, which in this paper is great. You try to implement the same thing, and you end up with the performances that you see there on the right. So you end up with an error of 40%, while the authors ended up with an error of 20-something%. And the first thing that I've seen many students think about is, okay, maybe the authors misreported something, or maybe the results are not as good as they could be, or maybe the authors were just cherry picking their results. But this is actually, I mean, it could be the case, but it's very likely not the case. And the reason for it is because there's so many reasons why there might be a performance gap between the implementation that you have made and the implementation of the original authors. And very likely there are a lot of software issues and a lot of little tricks that might make the model work much better that you might not have implemented. The authors of these papers have spent a tremendous amount of time optimizing the code, and by optimizing this code, they ended up with something that worked really well, which might not be the case yet for your own code base. So why is the performance really worse in your model than other models? The most likely one is implementation bugs, and they can be really, really silly things. For example, you have a very small set of innocuous lines, like the ones here, where you have features being mapped into that variable, labels being mapped into another variable, and then you are training a model with the features and the labels. And you see that your model is not really learning anything, it's kind of plateauing, your error is around 50%. And then you realize that maybe this globbing operation, for example, is actually causing quite a lot of issues. So the globbing system itself, the way you're finding the files that give you the features and the labels, is giving you, for example, something that is missorted. And because it's missorted, it ends up, for example, flipping the labels around and swapping them, meaning that the system is trying to learn something which is chaotic and pretty much random. There's also issues with the choice of hyperparameters, and as you can understand, the choice of hyperparameters is very critical in the kind of work that we do. So if you look at this plot here, for example, models are very, very sensitive to hyperparameters. If you just have a little, obviously this plot is a pictorial plot, not really an experiment, but you might have situations like this where with a low learning rate, the model will learn very slowly, as the name says. High learning rate, it might learn much faster, but it might plateau too early because it got stuck in some sort of a local minima or plateau, maybe due to the very high learning rate. If you make the learning rate even higher, it can cause situations where the loss itself will increase rather than decrease, even though that's not what we're trying to do. While if you find an optimal learning rate, you can get performances which optimize faster than with a low learning rate, and also end up with a better performance in the end. So finding this good learning rate is something that is quite hard to do. There are other small things, such as, for example, different types of weight initialization that can have very, very, very different behavior when it comes to the network itself. For example, here you see that as a very small difference in the way you initialize your neural network means that one basically does not optimize whatsoever, while the other one starts optimizing pretty much immediately and ends up with a better performance. So the way you initialize your network is also very important, which is another form of hyperparameter. It's not really a parameter per se, but it's just a parameter that you use to configure your network. Obviously, there's other variables that impact the fact that your model might perform worse than the original one. For example, the data and the model fit that you have might be worse, but most importantly, the data set is very likely going to be different. Obviously, if authors are using some benchmark dataset, this will be less of an issue, but in many situations that is not the case, and because it is not the case, you end up with poor model performances purely due to differences in the data. And this is really, really crucial. I have to be very honest here. We normally think about doing a PhD or doing research as primarily around developing the models, and that is to some degree true, but it's also extremely important to have data which is of the appropriate quality, with the appropriate characteristics, and data that is very well understood by the person using it. so that any caveats could be mitigated at any point within the development process. This is a little slide which was extracted from this talk from Andrej Karpathy, where he's talking about what kinds of things do PhD students or engineers at Tesla lose sleep over. And most of the times PhD students think about models and algorithms and not about the data sets, while people, for example, at Tesla, which is obviously a company and is very focused on products, thinks mostly about data sets, and models and algorithms are a second-degree citizen. And the reason for it is because a lot of the issues that these models can have and a lot of the problems that they face are due to the lack of data. And the amount of time you might spend trying to improve the models can be greatly superseded by just making more data available to the algorithms. Obviously, in the healthcare domain, things are not that trivial. And in the healthcare domain, we need to be careful because often it's not possible to acquire more data. So obviously this balance will change depending on which area you're looking into. Self-driving cars, where people are driving all over the place and data is being collected at every second, might have very different requirements than, for example, the healthcare setting, where data might be a little bit more scarce or harder to label. There's many issues that are common between dataset construction. So when you're trying to build a dataset, the most common issue that we face, at least in the healthcare domain, is the problem of not having enough data. And this is really crucial and is something that needs to be solved and something that is currently being tackled in healthcare, because not having enough data is pretty much the source of a lot of the problems, as long as the software itself, the algorithm, is correctly implemented. Obviously, not having enough data can be fixed by adding more data. That is kind of the trivial thing. But there are methodologies that allow you to train algorithms without having as much data available to you. You also have other types of problems, such as the presence of class imbalances. So your data set might be very large, but the amount of labels you might have, or images that are labeled of a specific class type, might be very small, purely because the prevalence of that specific disease type might not be very large in the population. Another situation where this happens is, for example, with data coming from screening programs, where you might expect a very small percentage of the people attending the screening program to actually have the disease that they're being screened for. And in those situations, data sets might have to be enriched for specific types of phenotypes or diseases in order to get a slightly better class balance between the different class types. You also have labels themselves, which are noisy, and again, in the healthcare domain, this is incredibly prevalent. Clinicians misdiagnose patients all the time, either due to clinical pressures, lack of data, lack of information, or purely because the diagnosis itself is very fuzzy and very hard to do. So noisy labels are key, and having algorithms that can deal with the noisiness of labels without being completely thrown off by one single mislabeled example is something that is incredibly important in healthcare. The train and test distributions can be very different in terms of the distribution of the data itself. But all of these things about how do you improve the data is not really the focus of this specific lecture. So why is troubleshooting really hard in the deep learning setting? First of all, it's very hard to tell if you have a bug or not. Sometimes systems train, and they train okay, and the system improves the loss function, and the loss function is being minimized, just not performing as well as you would expect it, and you do not know if that's an issue with the implementation or if there's something wrong with the code. And again, that goes back to this issue that I was discussing before in a couple of slides back, when I was talking about backpropagation and about automated differentiation. Because the system is going to automatically differentiate anything you give it. If you give it the wrong equation, it will still optimize for it. It just will not give the right inductive biases, and it's not going to be optimizing for the right function. So it's probably going to still improve the loss function. The loss function is still going to go down, but it's not going to do exactly what you would want it to do. And there's a lot of possible sources for the same type of degradation in performance. It could be related to the data, it could be related to the model, it could be related to hyperparameters, it could be related to some hardware issue itself, a software stack having some bugs somewhere. There's so many different reasons as to why things can go wrong that makes troubleshooting incredibly complicated. This normally results in pessimism from the point of view of the researcher themselves. They normally think that their model is doing something wrong, that what they're doing is not working as well as they would hope. And the issue with all of this is that it creates this incentive to try to find new and more complex solutions when the very foundations themselves are often not doing really well, so they're not correctly implemented. So it's very hard to disambiguate between different types of errors, and it's important that we start simple and that we make sure that whatever we have that is simple is working well, so that we can gradually then ramp up the complexity. So rather than trying to find complex solutions from the very beginning, we need to make absolutely sure and be certain that whatever we have that is simple is working and is working well, so that we can always use the previous checkpoint, the previous model, as a benchmark for the very next step. So here is a little diagram giving you the strategy for deep learning and troubleshooting. You see it has many steps, and we're going to go through each one of them with quite a bit of detail. The first part is to start simple, implement and debug, evaluate your model properly, tune hyperparameters and improve model and data to make sure that in the end you meet the requirements that are needed, either defined by your clinician that you collaborate with, or some theoretical limit that you might have in your own problem that you're trying to solve. So as a quick summary of the lecture, and this slide pretty much summarizes all of the things we're going to go through. Obviously, we're going to go through them in a lot more detail. But the idea of starting simple is that you should start with the simplest model possible and data possible to make sure you can overfit and fit that data well, and that the system itself does not have any issues. So you need to be in a setting where you're pretty much bug-free. Once the model runs, you need to make sure you can overfit on a single batch and reproduce a very well-known result. Overfitting on a single batch shows you that your backpropagation is working, that your model can memorize your data, and reproducing a known result on a small data set also shows you that the model is doing what it's supposed to do, so you can then have confidence that what you've developed is correct. At the evaluation stage, what you want to make sure is that you can decompose the different sources of bias and variance and decide what to do next, and we're going to see what that means later on. We need to start optimizing hyperparameters of models. Often models can be very prone to small differences in hyperparameters, and this is often deemed to be an issue, but in reality, some models are just more brittle than others, and you need to make sure that you're optimizing for the right parameters. And lastly, improve on model and data itself. So if you can make your model bigger, you will start overfitting your data. If you make a model too small, you'll start underfitting your data. And one of the best ways to regularize this is by making more data available to the model, so that you're regularizing this underfitting and overfitting to balance out the complexity of the model with the amount of data that you have. So there's a few things that we need to assume. We're first going to assume that we already have an initial test set. We have a metric which we want to improve and that is well defined. And we have some sort of target performance, which is based on human level performance. Yes, there's many problems where humans are not the gold standard, but just for the sake of this lecture, we're going to focus on things where we can ask a human to give us the correct answer, either due to human labeling or their previous knowledge, or just because there is some theoretical reason to decide that that's the correct label. So we're going to trust humans and their definition of ground truth. And the reason that these three things are assumptions here, and they're pretty broad assumptions, I would argue that they're very close to true in most applications that we have in a healthcare setting. But they're important because many of these decisions that we're going to make in the next few slides require these three things to exist. Without them, a lot of the performance improvements that we're going to see and that we're going to test for would not be achievable. In the Start Simple section of the process, there are 4 steps. First of all, you need to start by choosing a simple architecture, use very sensible defaults, make sure your data is normalized, and you need to make sure your problem is simple enough so that these initial tests can give you results that you can trust. One thing that we need to do from the very beginning is that we need to demystify the types of architectures that we need to use for different problems. And the motto here is that we should start simple. So for every new problem, every image segmentation problem, every image classification problem, every sequence modeling problem, there is always a fundamental network, or there's most of the times at least, in some applications that might not be the case, but in most settings there is a fundamental network architecture which has been shown to work well, and that is simple enough to implement to make sure that everything else is working well. For example, if you're going to hard code a UNet or a ResNet or an LSTM, depending on the kind of problem you have at hand, those are things that are pretty much easy to implement, primarily if you keep them simple. And there's many implementations online in software packages like Monai that can give you very good and very robust and well-validated implementations that you can start from. They are fundamental networks, and they are there to act as a strong baseline. When these are working, only then should you consider using more complex networks. For example, I would really not recommend you start running, for example, efficient nets for the purpose of image classification, and you should probably start with simpler networks like ResNet, or even simpler than that, like VGG networks. Those networks are much simpler to implement, and because of this, they're much less prone to other issues that might arise later on. The second one of these steps is to use sensible defaults. This means we need to choose the right optimizer, activation function, initialization, regularization, and data normalization for your networks. And again, keeping on the motto of starting simple, you should just use base foundation decisions in terms of these defaults that would work pretty much well everywhere. So for example, in terms of optimizer, yes, there are many optimizers you could use. An optimizer such as stochastic gradient descent tend to give you the best results in many settings, but they're also much harder to make sure that you're getting the right hyperparameters. So if you choose an optimizer which is more hands-off, such as the Adam optimizer, you can then trust that with a relatively reasonable rate of learning, you would then be able to optimize the model you want without having to worry too much about learning rate scheduling and things like this. From the point of view of activations, you have activation functions like ReLUs, which are pretty much still the standard, even though many new ones have been proposed. Initialization techniques, such as the He et al. Normal initialization, or the Gollerot initialization for sequence models. All of these different things are pretty much the default everywhere. In terms of regularization and the way to normalize the data, you should very likely initialize with no data normalization and no regularization. This is to avoid other issues that might come from those steps. We'll see later on how to tackle these issues. The third step of starting simple is to normalize the inputs themselves. So normalization of inputs here means taking the data and changing it in some way so that they all have the same or more similar distribution. It's very important to normalize and scale the input data itself. What normally this means is that you should subtract the mean and divide by the variance. So if your input data, for example, is just a series of values, scalar values coming from a vector of measurements, for example, or it could be an image itself, you need to take the mean value of that vector, subtract that mean value, and then divide by the variance. And by doing this, you'll end up with something that is zero mean and variance of 1, which means all of the different input data sets, both being, for example, some flat tensor or an image itself, will end up with the same mean and the same variance, and that allows the network to then start from something which is always in the same range, which means things like, for example, the way you initialize a neural network becomes much more stable, because then all the inputs are in the same scale, and the scale of the weight initialization can then be the same for every single network you train. For images themselves, there's absolutely no reason why they need to be zero mean and variance of 1, as long as they're all roughly in the same range, and the range is relatively close to these -1 to 1 range is perfectly fine. For example, in a MR setting, You might not want to have negative values because MRI images are magnitude images. So you might want, for example, to scale them between 0 and 1, and that's perfectly fine, as long as they all are within the same range and the range is relatively small in terms of its numerical value. You wouldn't want, for example, to scale all of the images between 0 and 10,000, because then you would need to be much more careful in the way that you will initialize the rest of the weights of the network. The last step of this starting simple is that you should simplify the problem itself. This means that you need to think about what is the simplest version of the problem that you want to solve. That includes, for example, starting with a small training set and grow it slowly. For example, if you're trying to solve for a semantic problem, such as a semantic segmentation, an image segmentation, the number of examples can be very small because one single example of an image will have many labels, because each pixel or each voxel will be a label. So can you overfit on a single example? Can you then overfit on 2 and on 5 and on 50? And each one of these steps will tell you something different. For example, overfitting on one example will tell you that the optimizer is doing the right thing and that the model is able to memorize, which means the model has enough complexity to memorize a single example. When we grow this single example to 2 examples and then to 5 and then to 50, we're seeing how the model is behaving in terms of its capacity and its ability to memorize things. Obviously, you would want the model to continue fitting the data well, but it's going to get to a point where it has enough examples that the model is not going to be able to memorize the examples any further, and that's the point where it will start doing the learning that will extrapolate to an unseen data set. These numbers obviously are very different in classification settings. Normally you need much larger data sets for classification than you would do for image segmentation problems, purely because of the number of gradients you get for each one of the labels that you have. The other thing you could try is to use smaller images, less classes, and less heterogeneity. For example, if you have many thousands of images and maybe many disease classes and data coming from multiple sites, just start with something simpler. Make your images smaller by reducing their resolution, as long as that resolution reduction processes do not deter your model from doing its task, for example, that do not hide the pathology you might be trying to find. Reduce the number of classes, for example, reduce your problem to a 2-class problem that is simplified, and make sure that you don't use data from multiple sites that might have a bunch of other issues in terms of domain shifts and things like this. So you want to be able to create a simple setting where you are confident that the model can learn, where you're not going to see things like, for example, problems with memory, GPU memory itself, or ability to fit the data. The other thing you could try is to create a simple synthetic training set where you are absolutely sure of the labels because you created the dataset yourself, and also where you can expect certain types of behaviors by construction because of the way that data was synthesized. The second one of the steps of this large diagram after start simple is to implement and debug. Implementing bug-free deep learning models is actually surprisingly complicated. There are pretty much these 3 steps, which is making sure that your model runs and that it's running correctly, that you can overfit on a single batch, and after overfitting in a single batch, that you can reproduce some well-known results that someone else might have published before. So the 5 most common bugs that exist in the deep learning setting are these ones. And again, this is not my opinion. This is something that was captured as part of these Twitter thread that I was discussing at the very beginning, is that these 5 are the ones that people find the most often. The first of all is the incorrect shapes of your tensors. And the issue with that is that it can fail silently. So what this means is that the shape of your tensor, the amount of dimensions you might have in X, Y, Z, or the ordering of X, Y, and Z, and where the channels are and things like this. Accidental broadcasting, making sure that you're not broadcasting the tensors to different dimensions. All of these things can cause your tensors to change their shape. And sometimes, because again, these systems can be quite smart, they try to do their best to make sure that the code still runs, but it might be that the code is not doing the thing that you're expecting it to do. So making sure that the tensors are of the correct shape after every single operation is something that is very important. You need to make sure that you're pre-processing your inputs correctly. So for example, that you're normalizing your data and that you're not pre-processing your data too much to the point of destroying, for example, the content of the data itself. I've seen so many situations where, for example, people have created very complex augmentation techniques, which they believe are correct, and they then are spend days debugging a network to finally realize that some issue in the augmentation stack basically meant that the network was seeing pretty much blank images as inputs, which means there was nothing for the network to learn. All of these can be due to problems of input pre-processing. You might also have incorrect inputs to the loss function. For example, and this is again very, very common. I think pretty much everyone of the PhD students that I had in the last few years have suffered from this issue before of double softmaxing something. So if you apply a softmax to an output of a network and you apply the softmax again, that will cause issues. Giving softmaxed outputs to a loss function that is expecting logits, again, that causes loads of issues. And all of these things seem a little bit innocuous when you look at the mathematics, but because of numerical precision and a few other things, they do result in some very serious problems that pretty much mean that your code is not working, even though it's a very, very small fix. Another thing that might happen is that you might forget to set up train mode when you're training your network. So as you know, for example, certain types of operations, such as batch normalization, have different behaviors during training and during evaluation of a model. If you're not setting up your network for training, if you forget to do it, to set up the flag as training, then these different operations will not do their correct operation, and the model will not train appropriately. Even worse, when you then try to evaluate, because you trained your network in evaluation mode, some of the variables might not have updated, which means that at evaluation time, the performance might be even worse, even though at training time, it was reasonable. So all of these things are very complex, and you need to make sure that you are setting up your network as training mode when you are training, and as eval mode when you're evaluating the network itself, primarily when you're using operations such as batch norm. Lastly is the problem of numerical instabilities. Again, when many kinds of operations such as exponentials and logarithms are used, and divisions, primarily divisions by zero, they can result in infinites and nans, and these obviously can cause big havoc throughout your network. So network might be training really well, and then suddenly at some point there is a very low probability, and by very low I mean zero, and you take a log of that and suddenly you have a minus infinity, which is going to cause a series of issues downstream, which means your gradients are going to be none, and when you apply a non-gradient to a series of weights, you're going to end up with non-weights, and everything is going to blow up. And this obviously can be caused by many reasons. It could be caused by the data itself, by problems in the labels. It could be caused by bugs, but it could also be caused by the size of the batch or the amount of memory that is available in your GPU, causing the gradients to be very unstable. And because they're unstable, they can spike and create optimization settings where infinites or nans might arise from the network optimization itself. So you need to make sure that you apply some numerical tricks. For example, when you're dividing by a variable, which might become zero, that you make sure that there's some sort of epsilon regularizer so that the division by zero doesn't happen. And this epsilon regularizer needs to actually be small and behave like an epsilon and not just some other variable that your model will have. A general advice for implementing your model is to, first of all, to use off-the-shelf components. This is something that I recommend all the time. Rather than writing code yourself, do use and make sure that you're using as many things as you can from libraries that are available. Obviously, it's important that you understand what that code is doing. I'm not saying that is not. You need to understand what the code is doing. But doing it yourself means that you're more likely to introduce bugs than it is if you were to use a well-validated and well-implemented code base. There's also many other tricks that exist. For example, if you were to apply specific layers, for example, let's say you want to apply a dense layer, a fully connected layer. You know that a fully connected layer is defined as a matrix multiplication by a weight matrix, and then it gets passed through an activation function like a ReLU. So you could, for example, say, oh, I know what the mathematics look like, so I'm going to apply a math mult and a ReLU operation to the output of that matrix multiplication. And this is mathematically correct, but numerically, that's not necessarily the case. So there's many numerical tricks that go into the implementation, for example, of the dense function that make sure that that sequence of math multiplication ReLU is optimal and that we don't have any losses of precision, that the graph can be optimized and that multiple operations can be compressed with each other and run at the same time, things like this. So there's quite a complex ecosystem underneath, and the numerics are not the easiest thing to understand. So you need to make sure that you're using the functions that are well implemented by these engineers, where they've thought about all the numerical issues that might arise and implement them themselves. Another example of this is cross entropy. For example, if you write the actual expression itself, it's very likely that you're going to end up with very poor gradients, because the cross entropy, due to the use of logarithms and exponentials, it can cause quite a few issues in terms of the stability of the gradients themselves. The other thing you should try to aim for is to have a lightweight implementation. By using off-the-shelf components, your own code base, at least for the first version of the code you want to try, should be as small as it can be. So don't try to write many thousands of codes in a very complex ecosystem. Make sure you can have something running with as minimal possible lines of code as possible for version 1.0. And the reason that you want to do this is so that you can add complexity afterwards, but you can always start from a benchmark that you know is working, which means you can then always test against this benchmark as something that is going to give you the baseline performance and something that should never be worse than that. Obviously, there's a bunch of other things in infrastructure that will be much bigger. For example, if you were to use libraries like Monai, yes, that part has a large code base behind the scenes, but your own code can be very small, primarily if you're using toolkits like that. So the first step of implementing a bug-free deep learning model is to get your model to run. And getting your model to run is about making sure that many of these issues that we were discussing are tackled appropriately. For example, that there is no shape mismatch and casting issues, which you normally do by stepping through the debugger, that you don't have any out-of-memory errors, and also other errors that might exist that you can look into, things like Stack Overflow and the debugger itself to try to go through them. One thing that many people actually forget is that Python itself, PDB, is a very good debugger. And if you're using toolkits such as PyTorch, you can use PDB or iPDB, which is a slightly improved version of it, to go through your code, to set a trace, and to go through the stack and just step through the code one by one. So you can actually use the Python debugger, primarily if you're using an appropriate IDE, like PyCharm or something like this, so that you can step through each one of the steps of the graph creation, and you can actually see the sizes of each one of the tensors, which are obtained when you are instantiating each one of the layers and linking them with each other. Option 2 is that you can actually step into the training loop itself. So not creating the graph that defines the network, but you can actually jump into the training loop and you can look at the loss, and you can go into each one of the runs, and you can then look into each one of the training operations, the gradients, and all of these other things. And obviously, depending on the kind of code base you use, if you're using TensorFlow or PyTorch, things will be a little bit different there. And if you are using TensorFlow, the iPDB does not work, or at least it didn't until very recently. I'm not sure if that has changed now. But you do have the TensorFlow debugger, which basically stops the execution just before the session.run, so that you can inspect the graph and make sure that everything is working fine. So all of these issues obviously can arise, and we were discussing quite a few of them. So we're now going to go through them very quickly one by one to make sure that we can get a good picture of how to tackle each one of these. Within the shape mismatch section, there's two types of common issues, the undefined shapes and the incorrect shapes. Depending again on the package that you use, undefined shapes can happen due to confusions, for example, between the different ways to obtain the shape of a tensor and the way you reshape the tensor itself, which can leave the tensor itself with an undefined shape. But you might also have incorrect shapes of the tensors themselves. For example, if you're flipping dimensions due to a reshape operation, if you take sums or averages or softmax along the wrong direction, you might end up with a tensor that is of the incorrect size. If you forget to flatten certain types of tensors after certain types of layers, if you need to get rid of some specific dimensions by squeezing a tensor along a couple of dimensions, or you might also have incorrect shapes due to data types, where data might be stored in one type and not be properly casted to a different type. Casting issues can also happen on these models. For example, if the data is not floating point 32, again, depending on the type of toolkit that you use, if you do not cast your images to the same data type, then it might be that many of the operations inside of the networks are happening with a wrong data type, and that can cause issues, not because the operations are wrong or the network is doing the wrong thing, but purely because that's not what you might want to do. For example, you can do int8 operations on networks, but obviously the behavior of a network is going to be very different if the data is int8 or if the data is a floating point 32. Another issue that can occur is out-of-memory issues, which are mostly driven by these four types of common issues. The tensor itself is too big, there's too much data, you're duplicating operations, and there's other processes on your machine. So the tensor being too big is normally the issue caused by the fact that your batch size might be too large, for example, or that you have a series of fully connected layers, and because your input tensor is too large, the fully connected layers is going to end up being really large, and because it's going to be a full matrix, it's going to cause a situation where you run out of memory. The too much data issue is caused by the fact that in many settings, people, depending on how you load your data and how you queue your data, you might be loading all your data into computer memory. And this obviously works well if your data set is small, but if your data set grows too big, you end up in a situation where your data is too big to fit in your memory, and you need to create a buffer. You need to make sure that you're loading your data properly with the methodologies that are provided by your tool package of choice. You also have situations where you can duplicate operations. For example, if you're creating a model, you might not realize that you're instantiating the model multiple times, and because you're instantiating the model multiple times, you're creating multiple copies of the parameters of the model, and that itself might deplete the GPU memory very quickly. And the last part is obviously you can have other things running on your computer which you don't realize. For example, having your GPU, which you'll normally use to train your models, also being used as a visualization GPU connected to your screen. So if your GPU is being used for both, then there is some memory that is being reserved for your operative system to be able to visualize the graphical user interface, and those things might interfere with the rest of your model training. There are other common errors also here, such as, for example, bugs, the way you initialize variables and forgetting to initialize variables, forgetting to turn off biases when using batch norm operations. And you also have other situations such as, for example, this fetch argument has invalid type error, which if you are a TensorFlow user, you might have seen it a few times, which is when you overwrote one of your operations with an output during the training session. The second one of the steps of these implementing bug-free deep learning models is to overfit on a single batch. So overfitting on a single batch, as I was saying before, gives you many different pieces of information. You have situations where you overfit on a single batch and the error goes up, the error explodes, oscillates, or plateaus, and they all tell you very different things. So for example, if the error goes up, it normally means that you flip the sign of the loss function and gradient, or the learning rate is too high. It might also mean that the softmax has been taken over the wrong dimension. If you're overfitting on a single batch, you'd expect the model to be able to memorize the data, if your model is complex enough, obviously, which means you'd expect your error to go down and to go down sufficiently. If it doesn't, it's because something else is clearly wrong. If the error explodes, by exploding here, what it means is goes to none or to infinity, it normally means that there's some form of numerical issue due to the use of exponents and logarithms and also division operations. It might also be caused by an interaction between these operations and the fact that the learning rate might be too high. That you can use this as the opportunity to figure out what a reasonable learning rate is and how to regularize and change the numericals of these more complex operations to make sure that you have stable gradients and that they do not explode on a single batch. If the error oscillates too much, and by oscillating, what I mean is not really getting optimized, it's just going up and down, up and down, up and down, normally that means that the data or the labels themselves are corrupted. You would expect if the data was always the same, because you're overfitting on a single batch, that the system would be stable. So if there is oscillation, it means that there is some source of stochasticity that is being introduced into the model. Either the labels are getting shuffled or something random is happening to the images themselves, which is causing the model to oscillate. It might also be due to the fact that your learning rate is too high, so it's causing the model to bounce between two of the sides of the valley of whatever landscape you're trying to go down in terms of the loss function. And the last one that happens is that it plateaus. Normally when it plateaus, it has to do with several things. The learning rate might be too low, so you're going too slowly, and because of this, the model ends up plateauing and not really optimizing. You might be in a situation where the gradients are not flowing through the model. So for example, if there's too much regularization, or for example, if your network does not have residual operations, it might be that the gradients just disappear due to the gradient vanishing problem, and that results in the errors plateauing. This was an issue very much at the beginning when networks were very deep and res nets were not known, and in those situations errors were very prone to plateauing due to vanishing gradients. You might also have the incorrect type of input to loss functions, for example giving softmax to a loss function that is expecting logits and things like this, and the label and the data itself might also be corrupted. All of these could be symptoms of the model having issues when you cannot overfit on a single batch. Obviously, if the error goes down, then you know you are overfitting on a single batch and the model is doing what it's supposed to do. If the model goes down when you're overfitting on a single batch, that does not mean still that your model is doing exactly what it's supposed to do. It just means that at least those very fundamental issues are not there, but other issues might still be there. So the next thing you need to do is to compare the result you got or the network that you've implemented with some well-known result or the original publication result. And here is where it starts getting tricky, because as we were discussing before, there's so many details that you need to go through so that you can make sure that whatever you've developed is comparable to what the original authors have done. So when you are looking into other people's results, there's a hierarchy of results that you need to have in mind every time you want to compare what you're doing to what other people are doing. So for example, you need to make sure that whatever you want to compare is not just someone's paper with no code or just a very simple baseline. You need to make sure that whatever you want to compare it to is an implementation of, for example, an official model that has been implemented and evaluated on a dataset that is similar to the one that you have. So for example, if you want to train a network to, detect diabetic retinopathy from funded images, for example, and if there's an implementation of someone trying to do a similar thing with a dataset similar to yours, and there's an official implementation of that model, then that's a very good place to start. And that's a very useful resource because you know it's the same model and the same dataset, which means you should be able to achieve the same degree of performance. If the model is an official implementation, but the dataset is not relevant to you, it's just a different dataset, is still important because the model is still implemented by the original authors, and even though the dataset is not the same, many of these datasets have similar inductive biases, so you could expect something that works on dataset A to also work relatively well on dataset B, unless the model is too specific to the dataset. If you now have an unofficial model implementation, these are very common in the deep learning world. Some researcher somewhere decided to re-implement a paper that is being highly cited in a framework that no one has implemented before. Let's say the official authors implemented their code in TensorFlow, and someone re-implements the same code in PyTorch. So for example, the PyTorch code might be available, but not the original official implementation. In that situation, you have an increased risk, so that implementation is less useful, and the results of that implementation are less useful. And the reason for it is because there is no guarantees that the person that has re-implemented that code has achieved the same degree of performance as the original implementation. For the same issues that we were describing before, there might be bugs, the data itself might be different, and also many of these small details that you might decide to do or not do when implementing these networks might change the network behavior very severely. Obviously, it might also be the case that the person re-implementing the code is really, really good and knows exactly what they're doing, and they might end up with a code base that is better than the official one. This is less common, but it can happen, so you shouldn't necessarily be deterred by the fact that this is an unofficial model implementation. The next level down is the results of a paper, and the paper doesn't have and doesn't provide any code. You should trust the results of a paper, but it's always very hard to know exactly what the authors have done, because obviously papers have limited number of pages and implementation details can make a huge amount of difference in the performance of models. You can also look at the results of your model on non-relevant datasets, results from a similar model on a similar dataset, and also super simple baselines, such as applying some very basic machine learning models to your data. All of these things are results which are important for you to compare to, and they're baselines which are important for you to compare to. But so you should really think very broadly about the different types of things that you can compare your models to, and not just the official implementation. Everything needs to be taken with a grain of salt, but at the same time, there's many different sources of information that you can compare to make sure that what you've done is correct. So just as a quick summary, the steps of getting your model to run, overfit on a single batch, and then compare the results can be summarized in stepping through your debugger, figuring out that if the shapes and castings and out-of-memory errors are all correct and all done properly. We need to make sure that the step of overfitting on a single batch, that you are looking for corrupted data, over-regularization or issues with broadcasting, and make sure that you keep iterating until your model performs up to the expectations, primarily when the expectations are good sources of a reasonable performance that you would expect your model to have. So we've seen start simple, and you've seen implement and debug. The next step is evaluating models. What I mean here by evaluating models is that normally when we think about training curves, we would like to see training curves that look like these. So you would have three training curves from the algorithm, and one of them which is defined by your human. You would have your train error, which is normally the one that is closest to the human level performance. You'll have your validation error, which is the one that will be closest to the train error, but normally slightly worse because the train error tends to have some degree, even though in some certain situations very small, of overfitting. And lastly, the test error, which tends to be slightly worse than your validation error, because obviously is not being used at all for hyperparameter tuning. Obviously, this assumes that all of the data comes from the same source, which might not be true. So if all of the data comes from the same exact source, then you basically end up with a series of errors. The first of them is that there is an irreducible error, which is the error that your human level performance or your humans themselves have. So if humans, for example, make the wrong decision 25% of the times, and you're using your humans as your ground truth, then you would not expect your model to be able to perform better than those 25% because your ground truth has that degree of error anyway. So even if your model is performing better than humans, you don't have a way to demonstrate that because your humans have that error rate anyway. Obviously, you could use things like consensus between multiple humans, but that's a different thing that is not part of this discussion. So the irreducible error and the train error have a certain degree of error, right? Which is the avoidable bias that the models have. This is normally caused by underfitting. So the train error should reach the irreducible error because the train error is something that you can overfit on. The train error will be slightly worse than the irreducible error if you are underfitting your data. If you are overfitting your data, then obviously your train error might be better than your irreducible error. But the reason for that to happen is because your network is memorizing those examples and they're very likely not going to perform very well on the validation or the test set. Between your train error and your val error, what you're measuring is your variance, so your overfitting capacity. So if you're training on a certain training set and you're validating on a different data set, the difference in performance that you have between train and val is going to tell you how much you've overfit to your data. So if you did a good job and you are not overfitting to your data, then you expect this difference to be zero, and it can be zero. But if your model, for example, is too big or not appropriately regularized or you don't have enough data, then if your model starts memorizing your training set, it normally would mean that your validation set will end up in a overfitting setting, or model will end up in an overfitting setting, meaning that your validation error is going to be larger than your train error by a significant margin. And the last part is the val to test error difference, which is going to tell you about the val set overfitting. So the validation set obviously exists so that you can optimize for certain hyperparameters, but the process of optimizing for hyperparameters of a val set means that we are using the val set itself and the performance in the val set to define what are the best hyperparameters, which means there's some degree of validation set overfitting. So the difference between the validation error and the test error is the degree of overfitting that happened due to the choice of hyperparameters or any kind of other parameters that might have happened in the validation set. So under the assumption that all train, validation, and test set data come from the same distribution, then the equation pretty much looks like this. So the test error is the irreducible error plus a biased part plus a variance part and the validation overfitting part. And that should get you the performance of your algorithm. Obviously, if all the data does not come from the same site, from the same distribution, and this again is very normal in the healthcare setting, where the training data and the test data might look slightly different due to differences in acquisition or different phenotypes or different human characteristics, for example, you might have performance curves which are a little bit harder to read. And in that setting, one thing that you can do is to actually create two val sets. In this case, you can have a test val set and a train val set. These things look a little bit like misnomers. It's a little bit weird to explain it like this. But the way that I like to think about it is here train and tests mean data sets that you're going to use to train your model. So in this case, the source domain. And test set might be something that you use to test your model, which is going to be a target domain. So if there is a shift between your train and your target domain, having a train val error and a test val error will give you the degree of domain shift, as we understood a few lectures ago when we were looking at classifier performance as a way to characterize the degree of domain shift. So in this setting, if we were to look at a plot of a couple of slides back, you now see here that the train val error and the test val error, the difference in performance between these two, which in this case is just 3%, is telling you exactly the degree of distribution shift. So distribution shift can be mitigated in certain ways, but that tells you that there is a source of distribution shift, which explains part of the test error that you're observing. Let's say we have a task here, which is looking at some people's brains. Are they healthy or do they have lesions in their brains? So detecting if there are or not lesions in someone's brains, let's say, is a high performance task where humans can achieve a 98% classification accuracy. So the goal performance is that there is a 2% error. So that is the target performance that humans will achieve. If you were to train a model and the model will end up with a training error of 20%, that is a definition of underfitting. It shows that your model on the training set has a performance drop from the goal performance of 18%, and that is the degree of underfitting that your model has compared to the expected performance of your data. That normally is solved by things like, for example, increasing the size of the model or having models that are more complex and with more nonlinearities and more capacity. The gap between the train error and the validation error tells you about the degree of overfitting. So it tells you how much you've overfitted to the training set compared to the performance on the validation set. So if you were to underfit too much, for example, as is presented here, normally there is a slightly less risk of overfitting too much between the train and val. It's normally hard to get both the validation error and the train error to be low, but in certain situations, the train error can be low, so it's not underfitting the data, but there might be an even larger gap between the train and the validation error, causing even more overfitting. And the last part, there is a validation gap and a tests gap of around 1%, which is exactly what you'd expect. So between the validation and the test set, there is a very small drop in performance, which means your model at least is being correctly trained because you know that your validation performance is representative of your test error. So in the end, the equation is going to look like this. Well, you'll end up with a test error, which is comprised of the reducible error, the bias, the variance, the distribution shift, and the validation overfitting part of the equation. And all of these can be mitigated one by one. The next step is we're going to look into improving model and data itself. You can first address underfitting, address overfitting, address the distribution shift, and also rebalance datasets if applicable to your problem. In a underfitting setting, what you want is to reduce the bias that your model has. There's a few things that you can try, and the order that you should try them is presented here. The very bottom ones are things that you might want to try, but maybe at a later date only, and they should only improve things by a very small amount. But the first thing you should try, obviously, is to make your model bigger. The reason you might underfit and not memorize the data is because you don't have enough parameters. A well-trained model should be able to memorize data if the data set is small enough. So for example, if you make your training data set very small, this means adding more layers, using more units per layer, basically making the model bigger and adding more parameters. If your model has a significant amount of regularization, you should reduce that regularization. Next step is to do error analysis, which basically is the process of looking at what the errors are and figuring out why is the network failing. Choosing a different model and architecture is kind of step 4, and only then should you start tuning hyperparameters and adding features, because many other things should have a much bigger impact in terms of addressing underfitting. So if you were to add more layers to a convolutional neural net, what you'd expect is a behavior like this. So you'd expect the training error to go down from 20% to 7%. So there is much less underfitting because you've added more layers. And because there is less underfitting, the model is now fitting the data better. I mean, there is still some degree of underfitting. And normally, if the model is underfitting less, the validation performance should also improve. Yes, it might happen that the gap between the train and validation error has increased. For example, here, the train and validation error in the previous column is between 20 and 27, which means a 7% drop. While with a new model, the amount of overfitting that exists between the training and the validation error is around 12%, which is larger than before. But in the end, the performance of the validation error is still better than the original 27%. So everything has improved, even though the amount of overfitting has also improved. If you now switch to a better network, which has more capacity, for example, you might then see something like this, where again the train error goes even further down. Again, the amount of overfitting might be reduced or improved, so you might have the validation error drop between 19 and 10%. So again, the model has improved quite significantly and is now approaching the goal performance. If you now tune the hyperparameters, you might end up with something like this, where the train error is actually marginally smaller than the goal performance. I only put this number here of 1.8 to make sure that you understand that this is possible. Is it statistically significant? Very likely not. It might be caused by many other issues, but it is possible that due to statistical fluctuations and the size of the test set, you might end up, or the training set, you might end up with a training error which is lower than the goal performance, and that's because the model is memorizing things too much. And now you've seen that the validation error has been shoot up to 12%, and the test error is also gone to 12%. So tuning hyperparameters here has resulted in a lower training error, but actually a larger validation error and test error. So the way you're tuning the hyperparameters might not be great, because it does mean that you're overfitting the training set even more than you were before, which is causing a larger overfit gap between the training and the validation set. This is something that you need to be careful about and make sure that when you're tuning the hyperparameters, you're not resulting in situations of further overfitting of the data. The second step is to address overfitting. So we've been looking into underfitting. We're now going to be looking into overfitting the data. Again, there's a sequence of steps that you need to go through to reduce variance. The very bottom ones, again, is not something that I would advise, but the top ones, they're definitely something you should go for. So if more data is available, you should always add more data. That's one of the best ways to control for overfitting, is to make sure that data is there. Data is one of the best forms of regularization. You can add different types of normalization, like batch norm and layer norm. They can tend to correct for a lot of the overfitting issues. Batch norm can be tricky in the medical setting, but it's still very powerful. Add data augmentation. Augmentation is almost a free way to create more data. And there are ways to augment data that are so powerful that they can make the amount of training data needed to train a model properly be much smaller than what it was without augmentation. If you are using regularization, you should maybe increase that a little bit more, be it dropout, L2, or weight decay regularization. And this is really for models that are large and that are using fully connected layers. For convolutional models, this might be less of an issue. You should look into error analysis, trying to understand where the errors come from and what is causing the errors. It might be an issue with the data itself, or it might be an issue with the model not picking up certain types of things, which could then give you insights as to what to improve. The other step that you could do is to also use to choose a different state-of-the-art model and architecture, and to tune some hyperparameters. Things like early stopping or removing features or reducing model size, they are often suggested as ways to sort the problem of overfitting. Is not something that I would personally suggest. If a model is well trained with sufficient data and with appropriate architecture and normalization and augmentation, you shouldn't expect techniques like early stopping to significantly improve the performance, unless we're talking about some very special models like GANs, which can often benefit from early stopping. So in this kind of setting, again, you might have a situation like this, where you start a model which has a goal performance of 2%, train error of 1.8, the validation of 12, and the test error of 12, right? So this is the last model we've seen as part of the underfitting section. Now we need to reduce the difference between that 1.8 and that 12%. This is the overfitting part that we're trying to reduce now. So if you increase the data set, for example, what happens is that your train error will fluctuate. So it might go from 1.8 to 2.5. So it becomes harder for you to overfit on your training set, which means your training set is now going to be more robust and it will extrapolate more to the holdout set, which is the validation error. And that's going to end up with a 5% validation error and a test error of 6%. If you are now to add weight decay, for example, you will then, this is just a small form of regularization, you again will make your training error slightly worse again, but your validation error slightly better, which is again what you want in the end. And maybe this is your last result where you add some augmentation. By adding augmentation, your train error again stays the same, maybe gets a little bit better. Validation error continues going down. And if you tune the number of layers, optimize parameters, weight initialization, kernel size, all of these other things, you might end up in a situation where everything is 2%. And this is the holy grail, right? Where your train error is the same as your human performance, which is the same thing as your validation error, which is the same thing as your test error. The reason this is ideal is because it means that your algorithm has matched the human performance, that there is no overfitting and there is no underfitting because the performance is exactly the same on the train and the validation error, and that your cross-validation setup and model training setup has performed well enough that on the absolute test holdout set, it still achieves the same performance of 2%, which is your goal performance. That means you've met all your criteria when it comes to the performance of the model itself. In terms of improvements, the third step is to address the distribution shift. This is a problem that we've been looking at in the last couple of lectures, but it's something that you always have to take into account. One thing that you need to do, and again this is a series of steps, is you need to make sure that you are looking at the errors between your test and val set and make sure that you can collect more data to compensate for those errors. It's very likely that those errors are caused by specific peculiarities in the data itself. So collecting more data is normally the best solution to tackle those. If collection of data is not possible, you can always synthesize more training data to compensate. And only then should you probably start thinking about domain adaptation techniques to the training and the test distributions. And that's because domain adaptation techniques are ways to bridge domains, but they're also ways that are still going to be brittle to new domains that you might not have seen before. So you might bridge between domain A and domain B, but if now you are presented with domain C, you're going to have the same problem again. So having more data would mean that the model creates an intrinsic domain distribution shift robustness, and that will very likely mean that it will then extrapolate more and better to newer domains. And it's really important that we understand how to prioritize these improvements. For example, and again, this is all hypothetical. Let's say that you have an image which has an error in terms of ability to classify something due to lack of contrast in the data. So if the data itself lacks contrast, so you cannot see the object well enough, and if the error is relatively small, that comes from that kind of error. So let's say you have a 0.1% train validation error due to lack of contrast. The solution to do this, to improve on this error, would be to collect better data. Collection of better data is going to be extremely time consuming, and the improvement is going to be minimal. So this is something that you should give a low priority. If your data has a lot of artifacts, for example, and the error percentage that you might have might be 0.3%, first of all, you probably should collect more data with artifacts so that your model learns how to deal with artifacts. You should add synthetic artifacts to the training set, and you probably should try to remove some of the issues, for example, when segmenting an object, as some form of pre-processing or post-processing. So because there is a reasonable amount of images that do have artifacts, and we're talking about a 0.3% error, you should probably give this a medium priority because something that is technically possible and might have a reasonable impact on your model. If you, for example, have a domain shift, so there are changes in acquisition between training and test set, where your train val error might be 0.1%, but your test val error might be around 1% in terms of the differences in performance, then clearly this is something that tells you that you should collect more data for the new domain, which might not be possible, but you should try to do that. You should simulate or synthesize the new domain if possible, and also use domain adaptation techniques. And that's because we're looking at a test val error of around 1%, and it's something that is very well understood, such as changes in acquisition. And there are techniques that can compensate for that. So again, the priority of what to improve is a balance between the amount of work that will be necessary to achieve the potential solutions and the amount of error that exists between the test and the validation set caused by that specific error type. In terms of prioritizing improvements, the last step is to rebalance the datasets, which might not be applicable. So rebalancing datasets occurs when your your distribution on your validation set looks significantly better than on your test set. That normally means that you have overfit on your validation set. Overfitting on the validation set can happen primarily when your validation set is quite small and you have a lot of hyperparameters to tune. So if your validation set is small and you're optimizing all of these hyperparameters, you're pretty much almost overfitting on your val set via the hyperparameter tuning setting itself, which means your val set becomes less valuable because it does not actually act as a validation source. When this happens, you need to make sure that your data needs to be rebalanced. Rebalancing here means the partition that you initially made, for example, the very common 60-20-20 partition between train, test, and val, you might want to do something slightly different where you might end up with a 50-30-20 so that you can increase the size of the val set and so that you can also then convey more stability to the hyperparameter tuning that is happening on that val set. The last one of the steps of troubleshooting is to look into tuning hyperparameters. So tuning hyperparameters is something that everyone should be doing, but is one of the very last steps because it's almost a free improvement that you would get, but is also something that will give you an extra degree of stability in terms of how the models will work and train, and will remove a little bit of the human biases from how you optimize for these parameters. So when you're developing these models, there's many choices you need to make, all the way from do you want to use a ResNet, and if so, how many layers, what kind of initialization, kernel size, optimizer are using Atom, and if so, what batch size, learning rate, regularization, etc. I mean, all of these things are decisions you need to make. And they are all hyperparameters. The definition of hyperparameter is a little bit fuzzy, but hyperparameters is any choice which you can make when designing one of these networks. And how do you make sure that you are deciding on the right choice? The important thing to consider is that your choice of hyperparameters to tune is actually quite important. Some hyperparameters are going to be more sensitive than others to improvements in performance. For example, the choice of learning rate can have a very high sensitivity in terms of your overall performance of your model. So your model can change significantly due to the choice of learning rate. Optimizer might be less of an issue. Yes, you need to choose a reasonable optimizer, but is likely not going to cause a gigantic difference. The other optimizer parameters, such as the beta 1 of the Atom optimizer, are likely going to have an approximately low impact, primarily compared with the learning rate. The way you initialize your network is going to have a medium impact, and that's because you need to make sure that your network is appropriately initialized, and every network might be slightly different on the way you optimally initialize it to make sure that gradients are flowing through. So it's something you need to look into. Loss function, obviously, that's your target performance. That's the thing you're optimizing for. It's going to have a big impact. Obviously, the loss function might also be associated with your ultimate thing that you want to measure. So you need to be careful on how to choose these. The depth of the model is going to have a high impact or a medium impact here, but it's going to have a significant impact. The layer size is going to have a high impact. The layer parameters, a medium impact. Weight to regularization, medium, and nonlinearity, a low impact. So this is just to give you some, again, these definitions here of what is low and what is high is a ballpark opinion, but it's just to give you a little bit of an insight as to where you should be focusing your efforts so that you, for example, don't spend too much time optimizing for the Atom hyperparameters that are not learning rate, when in reality the learning rate is where most of your effort should go into. The first method of doing manual hyperparameter optimization is what is called the manual method, right? So the manual method is gradient descent by PhD. So you ask a PhD student to test different parameters and to basically minimize some loss function, the target function, by using the student itself to minimize those parameters. Obviously, this is a bit of a joke. What I'm trying to say with this is that a lot of the human knowledge that students develop when developing these models can provide quite a lot of insights as to the optimal choice of hyperparameters. So the students or postdocs, any researcher will understand the algorithm well, will understand what makes it more or less stable, train it faster and slower, and that means they will be able to tweak and change hyperparameters and probably get a reasonable solution by tweaking those hyperparameters by hand. If you look into many networks, primarily in settings where the computational requirements to train networks with many different hyperparameter realizations would be too cumbersome, choosing hyperparameters by hand is pretty much the standard. I wouldn't be surprised if many of you would just train one model with a reasonable set of parameters that you've tried a few times and they seem to work well. And the reason you've chose those is because you have some insights as to how these algorithms would work. So for a skilled practitioner, it might require less computation to get a good result because you know roughly which parameters are okay. But the disadvantages obviously is that it requires that you understand the algorithm well. And for basic networks, they are now well understood, but for complex networks, that is not necessarily the case. So it's very hard to actually get good insights as to how a new algorithm works. It's also very time consuming because it requires this deep understanding, which might not be available at ease. The most common way to optimize hyperparameters is to just do a grid search. This is where you, for example, try different hyperparameters for learning rate, different hyperparameters for batch size, and you try them with different spacings between them and different combinations. So this is super simple to implement and can produce good results, but is not very efficient in a way that you need to train all cross combos of hyperparameters. So the grid search might be very large and might require prior knowledge about the parameters to get really good results. So you still need to have a relatively reasonable range and a relatively reasonable distribution within that range. For example, you might want the learning rate to be in a logarithmic scale so that you are crossing multiple orders of magnitude, while, for example, the batch size might be, for example, in powers of 2. I don't know. Something like that is something that is part of human knowledge that will need to be included in the way to design this grid search. Another method, which I think is very popular, is to use random search, or a slightly improved version of random search which will be the course to find. So many different pieces of research have shown that as long as you have enough samples, random search tends to be better than grids. That's because it has less assumptions. The reason that is often less used is because people don't really like the idea of random search very well, primarily because randomness introduces stochasticity, which means that often results in results being less reproducible than they could have been if it was a very stable grid. You can also apply other kinds of techniques, such as the course to find approach. So what course to find does is it finds locations within the hyperparameter space where the model seems to be working better, and given those locations, it will then increase and the search within the specific subregion where that improved performance has been observed, so that it can get a more accurate optimal parameter in that region and while ignoring the rest of the hyperparameter space. It's a somewhat manual process in the way that you need to define exactly how the course to find search happens and the parameters of that itself, so it adds complexity, but it can give you very good results with relatively small computational burden. So just to conclude on today's lecture, deep learning is hard to debug because there's many competing sources of error. In order to train bug-free deep learning models, we need to treat building models as an iterative process. It's incredibly important that you start from a relatively small model and increase its complexity as you go along, so that you always have a foundation to go back to, and so that you can understand every time that there is a regression in your code base. And you need to follow steps so that it makes it easier to catch errors as early as possible. So as a summary, please start simple. Make sure that you implement and debug your code properly, that you have techniques to evaluate the performance curves, that your hyperparameters are properly tuned, and lastly, that your model is improved and your data is improved to make sure that you can deal with any issues that you might face from the point of view of under and overfitting, but also from the point of view of domain shifts. I hope that by the end of this lecture, you now understand better what to look for when developing deep learning models, the iterative process of developing the model and increasing its complexity, and how to read performance curves and what to expect of their behavior. Here are some additional resources going back to the Andrew Ng's book and the Twitter thread from Andrei Karpathy, which are two really incredible resources in terms of tricks of the trade of how to train these models. Thank you very much for listening. I hope you enjoyed today's lecture. And if you have any questions, just let me know and I'll be more than delighted to answer them.